Good morning, ladies and gentlemen. Let's go ahead and pick up where we left off from yesterday. Descriptions may be either qualitative or quantitative.
And what we're going to focus on today is the qualitative.
The qualitative. Sound spreads out from its source in expanding spherical wavefronts.
Sorry about the light show that's going on.
Yeah.
This is the basic idea of the geometry of sound. You have a source somewhere, yep, and they spread out from there.
They spread out from there in a spherical wavefront, kind of like that bubble we were talking about. How does the geometry of a sound wave inform our description of loudness?
Yep.
Let's go to our next slide. So this is a picture of a. Is it go? Oh my God! Is it crazy? I gotta see.
Look at this.
Oh, you poor things.
It pops.
So we're starting up with the projector. I'm looking at it right now, and I can see it like kind of oscillating between yellow and blue.
Yeah.
Anyways, my eyes. Okay, so in the middle we have that dark red color, and then right outside we have that dark blue color, which represents.
And that means the stretch and the squeeze.
Yeah, the stretch and the squeeze of the air particles.
The red is the squeeze, and the blue is the stretch.
And what happens is, as we go further out, the surface area of that bubble is increasing, right?
Yep.
And the surface area of the bubble is related to how much energy that bubble has. And the thinner the bubble gets, the surface area gets of that bubble, the less energy it has.
Yep. The energy is spread over larger and larger surface area, just like when you blow bubble gum.
And how does that affect how loud something is? Well,
absolutely.
It's less loud, right?
Yep.
The further it gets. And you guys have experienced that. A sound starts somewhere and moves like an expanding bubble.
Yep.
We heard this before, right? Oh, I need my thing. I always do. Don't forget the mouse. Okay, so check out this little simulation. Oh, sorry, I've got this going from my previous class. Okay, so right now the source, which is right here, has a velocity of 0, and the observer is also not moving. And let's go ahead and just play it.
So you can see the sound starting at the point and then spreading out.
Yeah, and it's moving, expanding like a bubble out.
Here, reset that. Let's see that again.
Okay, reset, and here we go.
And each pulse it sends out has the same center. And you get this, looks like an onion to me.
Ooh, sound like this girl. Ooh, reset. Okay, all right, and back over here we go. Oh, let me move this. I was making a video. I have to do a video for someone. I paused it because you got here.
Oh.
I'm leaving it up there though. Okay. Next slide. The center of the expanding bubble does not move.
It's like wherever it's born, that's where it's from.
Yeah, exactly. And so when that energy is released from that sound, you know, wherever that bubble is born, that initial bubble is born, it stays there.
Yeah.
The Doppler effect. Now, we haven't used these words yet, have we?
Nope.
Okay, the Doppler effect, that's what we've been talking about, occurs when the source of sound or the listener is moving.
And we can show them that on the simulation.
We can. So here is our Doppler effect. Let's go ahead and so the source is gonna be moving.
Give it some velocity.
Give it up there, okay. And here we go. That was a little bit too fast.
Slow it down.
Too excited. We'll go right there. And here we go.
It's still too fast.
Yeah, we need to be able to see the.
Yeah, do about 150. That's good.
I want you guys to pay attention to where the bubble is coming out from and what happens to the wavelengths in the front and the back.
So each bubble that goes out has its place where it was born, but the place where the bubbles are born keeps moving.
And check out let's look at this, the perceived wavelength of the observer. Okay.
So where the observer is right here, go ahead, hit it.
So boom. Okay, so the perceived wavelength is 0.55. What's the actual?
Come by pretty fast.
The actual is really 1. They're perceiving 0.5. Oh, and then once it passes, the perceived is longer.
So you see, it's a larger distance. So behind it's stretched out, but in front they're squeezed together.
Okay. And then what about the frequency? Hold on, it hasn't hit him yet. Oh, there, I guess that's it. Okay, perceived frequency is this really high number, higher than what it's supposed to be, and then it goes low. Ooh,
Yep.
You guys hear that? My stomach
Nope.
is growling. Okay, this is a really cool sim. All right, so the Doppler effect occurs when the source of sound or the listener is moving. So the listener could also be moving, but we're not going to get into it. If the source of the sound moves, bubbles with different centers expand.
Yep.
And we see that.
And we're really sorry about this light
I
show
know.
that's going on here, you guys. Sorry.
This is a short lesson. So,
Yeah.
the bubbles' edges get closer together in front, giving them a shorter wavelength and higher frequency.
Yeah. Yeah.
Write this down. This is important. This answers your questions from yesterday, your homework questions. The bubbles' edges get farther apart behind, giving them a longer wavelength and lower frequency.
Let's see that again over on the sim. Let's move it up to about 200 meters per second.
200 meters. Reset. And go to right. And we go.
So you can see in front they're closer together, higher frequency, and behind they're farther apart, lower frequency. Now,
And
go ahead. And why is that? Because the source is moving. It keeps sending out sound waves. Yeah.
And were we gonna show them this breaking the speed of sound thing? Maybe at the end.
Yeah, you can scroll up.
Okay, so we said
You
this.
scroll up.
We said you're right. It's up here, right? Oh, right here. So this is what we just were talking about here, and
This is at the speed of sound right
at
here.
the speed of sound, 343 meters per.
And what's
meters per
happening
second.
is the source is right on the front of the expanding bubble, so what you get is a shock wave, and then down below it, faster than the speed of sound.
And you can see observer one, boom, boom, right? Super cool. Okay, we'll go back over here. Super cool, man.
Super cool.
Okay. What's next? And it's colored. I didn't know it was colored. All I have is my lame black and white here. Okay. All right. We hear a higher pitch as the sound approaches and a lower pitch as it moves away.
Yep.
Right? And that's the thing with the high frequency and the low frequency.
So the car, as it comes, you hear nah. As it goes by, it goes nah. And the driver in the car hears a pitch in between.
Yeah. So how does relative velocity affect the pitch we hear? Well, Boykin brings up a good point. It depends where you're standing, right? If you're in the front, you're going to have that high pitch. If you're in the car, if you're behind, it's going to be that low pitch. If you're in the car, it's somewhere in
If
between.
it's coming at you or going away from you, that's the point. All right.
Okay, so you're going to do some close reading. You're going to go to page 440 in the AP Physics book.
And it's only going to be half the page. Start at where the paragraph says, if the stationary.
It's going to be right here. Okay, and you're going to read down, and this is going to give you the math explaining why the Doppler effect does what it does.
Yep.
And then for your homework, you're going to go to page 456 in the AP book. Right here. And you're going to read till page 459.
So do all this reading right now.
Go for it.